Hello everyone, welcome to Microcontrollers 1, How Silicon Thinks. I'm Mikolaj Lenczewski, and with me is Hakan Okten, and we will be presenting this masterclass. So, next slide please. So here is our syllabus. Right now we're in Microcontrollers 1, that's Friday. Next Friday we will have Microcontrollers 2, probably around 5, around the same time. And also the Friday after that, so the 11th, we'll also have Microcontrollers 3. That the timing on that one is to be discussed, but it should also be around 5. Next slide, please. So a brief definition of microcontrollers. So there are two very closely related kinds of embedded system: microcontrollers and microprocessors, and the difference is very subtle. So microcontrollers they come batteries included. They have a CPU, some RAM, flash memory generally, and peripherals that can be accessed, such as a USB interface. Um, Microprocessors can be considered as a subset of microcontrollers, where they only contain the CPU. Good examples of microcontrollers are the Arduino, the TNT family, and the STM32 and 8 families. Specifically, the TNT 4.0 is the microcontroller that we at Hyperloop Manchester are using, and we'll talk about that a little bit more in a later slide. The boards for microcontrollers generally come packaged either as a so-called development package, a dev board, or as a SMD component. Development boards are used where you want convenience and where you'd rather quickly iterate on your code, because they generally come with a USB interface to flash code onto the microcontroller. Whereas SMD components are more for finished products, where you burn the program using an external programmer, and once it's been burned, you don't touch it, ever really. When you've got a microcontroller, it can either run a so-called embedded OS, or it can run bare metal code. The difference between the two will be covered later by Hakan. Next slide, please. So here we've got two pictures. On the left is a microprocessor, the Intel 404 or 4004. And on the right is a microcontroller. You can see that the microcontroller has a lot more. I say a lot more. You can't really see the silicon in the microprocessor, but you can see that the microcontroller's die has a bunch of stuff in it, lots of different sections. Those correspond to the CPU, the RAM, and the peripherals. They'll all be housed on the separate segments that you see. Next slide, please. When you've got a microcontroller, the largest use would probably be in home appliances such as your dishwasher, your washing machine, even a Hue Philips light bulb. They're used to give intelligence to otherwise dumb appliances. The second largest use would be in embedded projects. For example, a DIY drone, homemade electric cars, those kinds of things, where you need to give some form of intelligence to your project. The microprocessors are used in these settings because they're light, they're cheap, and they're plentiful. They're replaceable. If one breaks or if you somehow manage to damage it, you can just swap in a new one very quickly. Furthermore, when you've got a development setting, you're generally using the dev board, which is the version that comes with batteries included. That's simply because it's more ergonomic to develop on. It's got the USB interface, it's faster to flash. It comes with a clock generally, so you don't have to add any additional components. You can just drop it in and break out from the dev board, and you got it working. For the appliances, they'd generally use the SMD components, and they'd integrate the clock and any other necessary peripherals onto the final PCB, separate from the actual microcontroller. They do that on their own. SMD components are generally cheaper because they have less silicon, they do less, and they're smaller than the dev boards. Their footprint is very, very much smaller. Next slide, please. Here's what we're using. So we at Hyperloop Manchester are using the TNT 4.0, which is an extremely fast microcontroller. It runs at 600 megahertz without any overclocking, and it supports the so-called dynamic clock range, which means that the internal hardware timers don't vary. They're fine and they're accurate no matter what clock speed you're running. They don't become less accurate as you overclock. That is a thing that happens on Arduino boards, where when you overclock your microcontroller, the internal hardware timers, they accumulate error. They stop being accurate because they designed with a fixed clock speed in mind. The TNC doesn't have that problem. The TNC also has loads of memory, 1024K of RAM, which is 128 times that available. Which is 1024K of RAM, which is 128 times what is available on the Arduino Mega 256, and also 2048K of flash memory, which is 8 times what's available on the Arduino Mega 2560. The TNC also contains loads of I/O with 40 digital pins, which are all interrupt capable. They can handle an interrupt when the pin goes high or low, and 40 analog pins. These pins there are separate pin groups, which allow the use of a certain interface with those pins. For example, there's 2 pin groups with SPI interface capability. There are 3 with I2C, 7 with serial, and 3 with CAN. Of course, you can also use your own pins. Those are explicitly mentioned in the datasheet. the TNC also contains a bunch of miscellaneous features, such as a cryptography accelerator. Say you wanted to do AES encryption, you could, and it would be fast. It contains an RNG, a random number generator, a real-time clock, the RTC, and also contains a pixel processing engine. Next slide, please. Actually, now Hakan, you will take over, and Hakan will explain to us the bare metal and the embedded OS that I mentioned earlier.
Yeah, thank you, Miko. So using a microcontroller with a bare metal is the conventional way to write the code for an embedded system. The process starts with writing the code, continues with compiling the code script by putting it to the microcontroller, which is currently in use. Then it continues with uploading it to the platform. But if you're using a development board, generally like uploading, it continues with uploading it by using USB. Finally, it ends with running and debugging the implemented program. While you're creating the software project, firstly, you need to specify the features you need for the project. To obtain and use those specific features, generally there are plenty of packages provided by the developers in IDEs, which is for integrated development environments, and created in order to cater the needs of the software project you designed. If the code you write is the code you compiled, then this kind of programming is called as zero overhead programming. So another approach of using a microcontroller is operating systems, which is called as OS in short, as Miko mentioned previously. There are various kinds of operating system, such as free RTOS, free real-time operating system, which is for free real-time operating system, and ROS, which is for robot operating system. Free RTOS is categorized as threading library. Using this kind of libraries can make concurrent operating easier on microcontrollers. Free RTOS has each task executed for from 1 to 10 milliseconds before switching. This means that there will be higher latency. Kinds of robot operating system are mostly used in autonomous systems, such as self-driving cars and autonomous flight vehicles.